Mongo for hosting us. We have 2 talks, but I think Joe wants to do a little talk about Mongo first.
No. I'm not going to bend your ears about MongoDB. I just want to say welcome. Yeah. We're delighted to host you here. We'll be happy to have you back. I was introduced to a meme I had not heard of before, which is that MongoDB is Snapchat of databases. Shameful, man. We'd like to ensure you that it's not the Snapchat of databases. It's designed to be a general purpose database. It's written in C++. We think it's an excellent choice if you need to change your schema. Your schema is changing during your project. That's what MongoDB really shines for. It will then scale out to 1 million nodes and 10 billion transactions a second and all that stuff. We're designed to be scalable. But mainly, the key value proposition for every program room is if the schema is changing, if your requirements are unknown, you need a database with dynamic schema, and that's where MongoDB shines. That's the end of the sales pitch. Anyone wants to find out more about MongoDB, I can tell you more about it later. We've got more pizza coming. We undershot on the pizzas because we were using our own estimates from our own MongoDB meetups. We're obviously a far more engaged bunch. So there'll be more pizza arriving before the break. And thank you for coming along. And isn't it great that the weather is half decent tonight? Help yourself to beers, and if you need anything else, just come and ask me. There's stickers down there. We have a database in the cloud. If anyone wants tokens to use that for some period of time for free, give me a shout. My name is Joe Drumgool. Take it away.
So first up, we have Bernard. Where is Bernard? Hey, Bernard. He's going to be talking to us.
Can I say one more thing?
Yes.
Otherwise, Margaret will kill me. We're recruiting all the time for C++ programmers. I'd be delighted to talk to you about that as well. That way, Margaret won't kill me. She's there somewhere. She was about to kill me.
I'll burn her up to talk about modernizing the MongoDB Codebase. Okay. Yeah.
Cool. Hey everyone, thank you very much for coming. My name is Bernard Gorman, and I'll be talking about the efforts that we've made in the past and ongoing efforts to modernize the MongoDB Codebase, why we do it, what the benefits are, and what we're doing at the moment to try and further that.
Bernard, you're going to have to speak up.
Oh, right, okay. How's this?
Better?
Better? Okay.
Louder is always better.
So a few quick words about my own role here. I'm a member of the server query team in Dublin. It's a team of 9 people, the bulk of which is in New York. The query team is responsible for, within the MongoDB Codebase, the CRUD execution path, which is built on top of the storage layer. It provides the query interface that's used by other systems like replication and distributed systems for performing local reads and writes, and basically a broad way of stating the query's purview. The query team's purview is that any logic which inspects and manipulates the contents of user data is ours. Specifically, we work on query planning, optimization, execution, the aggregation framework, which is MongoDB's way of transforming data through a pipeline in order to basically perform arbitrary transformations on it. Non-materialized read-only views, and we also own the CRUD path on MongoS, which is MongoDB's distributed routing system, basically. So if you have a sharded cluster spread across X number of different nodes, replica sets, the MongoS sits above that and does the actual query targeting. So I spent a lot of my time in the last couple of development cycles working at the intersection between query and distributed systems on things like change streams, which was a major feature released in 3.6. It's basically our offering of a real-time notification API. So anytime that anything updates or changes on MongoDB deployment, you get a notification of it immediately. So all of this is interesting. but it's interesting more in a kind of a general engineering sense. So since this was this is a C++ specific meetup, I figured I would kind of step outside the query system specifically a little bit and talk about how and why we make this effort to ensure that we're always at the forefront of keeping up with the most recent standards of C++, and how that has proven beneficial for the query system specifically and the query team. So, quick overview of the talk. First of all, why do we do this? We have a lot of other things to be working on, but we do make the time to push forward our compliance with the C++ standards and to rework areas of the code base that are older in order to conform to those. Then I'll discuss the history of how we've done this and how exactly it is that we go through the process of officially switching from one standard to the next. Then I will discuss some examples that are related to the query team and work that we've done. In other words, as it says there, cases where modern C++ made a difference. It allowed us to do things that would have been otherwise awkward or inelegant. Adhering to modern standards allowed us to solve these problems quite efficiently. And then I'll quickly go through some where we are now and what we're planning to do in the immediate future. And then probably some time for some questions at the end. Okay. Right. So why is this a priority for us, and why do we make sure that we're always as far as we can towards the current standard? So a couple of reasons. First of all, modern C++ makes it far easier to write reliably correct code. Things like, for instance, unique pointers and shared pointers, managed pointers that will clean themselves up and that have an inbuilt ownership model. Delegated constructors, which are introduced in C++11, meaning that you don't have to, basically write 5 different constructors and copy and paste half of your code between them all, which is nice. It encourages a more idiomatic coding style or stronger idiomatic coding style. So, for instance, in C++11, you can do things like SC all of iterator over your container, and then use a lambda to determine whether or not all elements of the container match some criterion. So this, for instance, is a single line, and it's a far more idiomatic form than the alternative, which would be to basically iterate over one element at a time and then check whether or not all of them are true and break. Thirdly, brevity of code implies readability and hopefully improved maintainability. So, for instance, if you take the first line there that explicitly, the trivial example, first line there explicitly sets out the return type of the function, which most of the time is fairly evident from the function name itself. We can just cut that, and if you imagine having to read through 10,000 lines of code that's dense with these explicit return types, it's going to be a string. Whereas we can just write in C++11 and on, auto, and it takes care of it, and really, no context is lost. A big one, performance improvements. So just by the act of moving to the latest standards, you get a certain amount of implicit performance improvements. So some of the notable ones are in moving to C++11, you have implicit moves. So basically, the standard library in C++11 is move compliant, which means that in cases where previously you would have been copying, now with the same code, you may have opportunities for the compiler to optimize that to a move instead. NRVO fallback, so in cases where NRVO isn't applicable previously, it would fall back to a copy, whereas in C++11, it will fall back to a move instead. C++14 extends the same concept by allowing you to also do an implicit move if what you're returning to has a move constructor, whereas previously the types had to match exactly. And then obviously, explicit SCE move where appropriate. So if you're writing a code and you use SCE move explicitly yourself, you can get huge performance savings. I'll discuss a brief example of that later on. Finally, but by no means least, Developer satisfaction and productivity. It's just far more pleasant to write modern C++. And that is, not worth nothing. Okay, so I'm not sure if you can see this very well, but I'll go through it anyway. So this is basically a timeline of milestones in our past modernization efforts. So we had in October 2007, the first MongoDB commit by Dwight Behrman, one of our founders, back in the bad old days, before C++11. From the perspective of modernization efforts, obviously, this was before C++11, but still the MongoDB codebase is only 10 years old, and it's been basically in fairly consistent development since then, which does facilitate modernization efforts as compared to perhaps other systems that might have legacy code that's going back far, far longer than that, that's essentially been walled off and signs put outside saying do not touch. So definitely the fact that most of the MongoDB codebase has been in active development over that entire period has allowed us to progressively update it as the standards progress. So in August 2011, C++11 was approved. That gave us things like auto type deduction, ranged for loop, braces everywhere, otherwise known as uniform initialization or universal initialization, or value references and std move, lambdas, constant expression, null pointer, constant, and delegated constructors. So this was obviously the big seismic shift in how in going from classic C++ to the modern era. So obviously our developers were immediately fascinated by this and really wanted to jump on board. But MongoDB 2.6, which was the release subsequent to the 2 releases after, I think, maybe a little bit more, was still on C++ 98. The codebase was still C++ 98 compatible, but by that point we had ensured that it was also building successfully on a C++ 11 build variant that we had running. The reason for that basically was that at that point, or in 2013, late 2013, when this was really being discussed, the compilers that we were using, modern compilers, GCC, Clang, and MSVC, didn't have complete support for all of the C++ 11 features. And so the decision was taken to stick with C++ 98 compatibility, ensure that we were positioned to move to C++ 11 when the compilers had a complete implementation of the entire standard. And the goal was to make the switch officially by 3.2, MongoDB 3.2. In the meantime, in August 2014, C++ 14 was approved. That gave us a couple of standard of living improvements, like automatic return type deduction, automatic lambda argument deduction, binary literals, a no exception specifier, and improved constant expression, which allowed us to use more language features in a constant expression function. So in MongoDB 3.2, which was released in December 2015, we officially moved to C++ 11 and removed compatibility with 98. You had to build MongoDB on C++ 11 from that point onwards. We subsequently backported that support to 3.0 and immediately began planning our move to C++ 14. Right. Fast forward to December 2017, C++ 17 approved. That gives us things like structured bindings, std optional. The MongoDB codebase makes very, very significant use of a couple of boost features, chiefly among them boost optional. So when we move to C++ 17, we're looking forward to being able to use this instead. Inline initialization of variables in if and switch statements. Automatic type deduction for containers, which is very nice, so no more having to specify std pair, angle brackets, massive line. it'll take care of that for you. And variable arguments in variable template arguments. So December 2017, same month, MongoDB 3.6 is released. We moved the standard forward to C++ 14. We also implemented a couple of C++ 17 polyfills in C++ 14, and again began planning for the next move. This is projected, MongoDB 4.0, not released yet, but coming soon. Again, C++ 14, GCC tool chain 6.7. Sometime in the future, 4.2, that's currently slated to move compatibility to C++ 17. And then late 2020 sometime, C++ 20 approved, and the whole thing will start. Okay. Right. So how do we actually go about making the switch? Considering that, obviously, as I mentioned, the code base is in fairly constant development, significant new features added and changes made and refactoring done between each version. How do we manage that? Well, we don't. The platform team does. The platforms team is another team within MongoDB. They are responsible for the toolchain and general developer ecosystem. Basically everything that we use, the other teams use to develop, they put in place. They're also responsible for a couple of areas of the code base themselves, security being one. They also handle the networking layer, I think, as well. They also function as an in-house C++ standards and practices experts group. These are the guys who, if you have a question about some very obscure feature of C++, you ask these guys and they will tell you the exact footnote in which draft proposal explains what you're seeing. I'm exaggerating, but only very slightly. So,
are these guys all in the States, or is some here?
These guys are all in the States. Yeah, unfortunately. This means I have to wait around 5 hours before I can ask them. But yes, one of their explicit functions in their charter is to act as an in-house experts group, basically, specialists. Sorry, I mentioned these are the. This is some of the tickets involved in the epic for moving to C++ 11, and this is some of the tickets involved in the epic for moving to C++ 14. So we do put some thought into it before we pull the trigger. Okay, so to outline the general procedure of how we go about this, we target a particular release well in advance. First of all, in the case of C++ 11, it was 3.2. In the case of 14, it was 3.6. In the case of 17, it'll be 4.2. And we introduce an optional build, the option to build against the next standard, the one we're targeting, in the dev cycle preceding the targeted release. So, for instance, when we were targeting 3.6 for C++ 14, we introduced the ability to build it to compatibility with C++ 14 in the 3.4 development cycle. And then basically when we cut 3.4 and branch to start development full-time on 3.6, that's the point at which we then make the switch, generally close to the start of that development cycle, so everyone gets used to it. So we add, at that point, we add a build variant to our continuous integration system, which we call Evergreen. We address any incompatibilities that arrive. So basically, before we actually change to the new standard, we've already been building against that standard successfully for a year, thereabouts, maybe more. We also, in certain cases, pull forward features from the next standard into the current development cycle that may be of use. The second, obviously, that may ease current development, but also it means that we may be able to write code now that will immediately translate to the official standard when we move to it further down the line. So basically, the platform team kind of proactively nudge us towards using things that they know are coming down the pipe. So yeah, again, this is not showing up very well on the board, but basically, build system ports at C++ 11, 2.5.0. Right, so that's the development branch leading up to 6. So that was back probably in 2013, I think. So that was, that was in the works for a long time before eventually being officially adopted in 3.2. This is 3.3.5. So again, that's close to the beginning of the development cycle for 3.4. And we add the C++14 variant. So we're building against it already and ensuring compatibility with it all the way through the 3.4 development cycle until we hit 3.6, and then we go, okay, now we're going to switch over. So some examples of some incompatibilities that arise that, really, they're quite difficult to foresee until you actually start doing it. Non-portable, vargs, comment deletion, constructing Mongo initializers facility. So basically, one of the very fundamental parts of the code base use this construction for variable args macro, and this double hash at the start is intended to essentially. So if you call the function with variable args at the end, you may have a couple of arguments, comma, and then this. So if you just use the VA args, essentially, if you don't pass any arguments to it for the variable args part, the comma remains, and you get a compile error because you've got comma in bracket. So this is a GCC extension, which in the event that you pass in no arguments will remove the comma automatically. So we've been relying on this for a long time. Fortunately, as we discovered, when you move to C++11, you also commit to the C99 standard. And C99 had its own version of this that is incompatible with this. So when we switched over to C++11, we basically had to rewrite our use of this in the code base in order to maintain compatibility and not to be using extensions that this is very widely supported, but it's not actually a standard. So those kind of things have to go. Here's another example from the C++14 cycle. Xcode to version 8 for 3.5 builds. So the problem here is that previous versions of Xcode, this is actually a holdover from C++11. Xcode prior to version 8 didn't support the thread local keyword in C++11, which meant that some of the work that we had planned for the changeover to C++14 to unify all of the different thread handling libraries that we were using, or the thread handling structures that we were using, fell over because this didn't support the actual standard. So before we could do that, we had to upgrade, make sure that we had all our build variants and upgrading all our tool chains to at least Xcode 8, and only after that point could we then actually coalesce all of these libraries together. So this is an example of pulling features forward that may be of use now. So this is before we actually made the switch to C++11, when we were doing optional C++ builds, compatibility builds in the previous development cycle. Introduce Mongo no-except macro for labeling methods like must and throw. So in C++11, we got the no-except keywords, which obviously does exactly what it says in the tin. So what we did here was we introduced a Mongo no-except macro, which basically did the same thing. The idea being that by introducing this and encouraging people to use it, it would ready the code base to just switch over to the standard when we then actually reached C++11. Similarly, this is again before we're officially supporting C++11. This is optional build. Give Mongo status move semantics when compiling into C++11 mode. So status is very, very, very hot in MongoDB because it's used essentially in most of our return values wrap an actual return value in status in order to signal whether or not the operation was successful. So you can get either successful operation and the value, or you get a failed operation and the value. So this is very, very, this needs to be lightning fast. This is part of kind of the core libraries that really needs to be performant. So very early in the development cycle, we said, okay, well, if we, in the case that we are building on C++11, we give it a move constructor, then we're going to see a significant performance, well, certainly a very worthwhile performance improvement from code that uses this, which is essentially everything. And oh, there we go. Okay. Some examples from the current we're currently on C++ 14, as I mentioned. But what we did in addition to this was implement our own versions, bespoke versions of some C++ 17 concepts or functions in C++ 14 so that we can start to use them. For instance, here, so in C++ 17, you have an asconst, std asconst, which basically, if you give it a value, you get back the cast. It gives you a constant value of that, the object back. So we implemented our own version of that, and it's already been used. I'm not sure exactly how extensively it's been used in the codebase at the moment, but it's in use. So when eventually we do move to C++ 17 again, that will just work. Okay.
I've got a quick question on this. I can't see it very well, but it looks like you're using ifdefs on the C++ macro.
Yes. Yeah.
Isn't that not very portable?
Well, this is basically what it's doing is it's just saying that if the current, if we're not building against C++ 17, then we use our own bespoke implementation of this asconst.
My point is that sometimes compilers will get, say, the R value X feature, but they didn't update that macro. So that kind of happened a few years ago, and libraries like Boost and Qt used to check the versions of compilers and then add a new defined, Boost underscore have R value X or something.
Right.
Well, first of all, do you consider using another library that already does this stuff, like Boost?
Well,
Boost config does this kind of thing, and
we do use Boost, as I mentioned, but we basically limit its use in the code base to only where it's really necessary. And I'm not entirely sure actually about this define here, but sorry.
Are you aware that Boost config is actually a standalone library that works completely independently of Boost?
I was not.
Yeah. So you can actually download it on its own GitHub. It's completely separate, standalone from Boost, and use it to do these things. And it's completely header-only copy. Dogmatic is a great programmer.
But to answer your question, I would imagine the approach would be to ensure that whatever the tool chains we're using for each platform actually do have this, and that it's going to be consistently available for us wherever we're building. Beyond that, I'd have to look into it further.
Some compilers only update that macro after they've implemented all of C++ 17, for example.
Right. So only once they've
release might have, I don't know, context with or whatever, but not update that macro, so then you'll miss it.
Right.
Maybe some people like that.
Well,
Also, compilers don't necessarily track their standard libraries. So, for example, at work, we are targeting this in C++ 4.4 using Plank 7.
Nice.
That works. Yeah, well, we can still pass 4.4 for various copyright reasons. But the point is, trunk tag works. But that's just fine.
But you also generally can't test the version of a standard library very easily.
Yeah.
So, how do I answer that question, or sufficiently? Okay. So where are we here? Right. Yes. So once we actually cut the next, so as I said, we've been building this all the way along through the development cycle. Once we actually cut the new release, generally, preferably quite early in the development cycle of the next version, we after we've branched, we remove support for the old version, require building with the new version, and then sometime after that, we begin adding support for the next standard. So introduce C++ 11, then we move to actually requiring C++ 11. Shortly after that, we start introducing support for building on C++ 14, and so on. So I put these slides in. I put these images in so we could actually see the dates when these went in, but I can't. So it's that's 3.10 and 3.35. So that's development for 3.2 and development for 3.6. Okay, so after we've officially made the move over, there's still some additional work to be done. Platforms team still doing yeoman's work. As I mentioned, we use Boost fairly extensively in the past, even more so. So the first thing that we do is any features of Boost that, as commonly happens, get obviated by the standard library. We either move to the standard library implementations directly, or in certain cases, we introduce a polyfill. Basically, instead of using Boost XYZ explicitly in the code, we hide it behind an STDX, and then first of all, we provide Boost implementations, but then secondly, later on, we introduce STD implementations of the same of the functions as well. There's been some discussion in the past about whether or not we should eventually just get rid of this and move to STD entirely, but generally, certainly in some cases, the feeling has been that having actually put these polyfills in place, they provide a fairly useful level of indirection against if certain platform for whatever unforeseeable reason in the future develops some sort of problem or is problematic in some way, then the polyfill layer gives us an easy out. So generally, we still do this. So features that we've pulled forward from the next standard that we're going to, they get replaced with their standard counterparts. And if this all has gone to plan, that should be a nothing. That should basically be search and replace, and because people have been using them for a year already. Sections of the code base, typically the ones owned by platform, up to the new standard straight away. Basically all this stuff. The goal is to update as much code as makes sense, but avoid unnecessary churn, obviously. You don't really want platform team to be going through the entire code base, upending everything and making sure that it's all, perfectly compatible immediately with the new standard. Some examples of this kind of work for when we move to C+11. So we're replacing alter pointer with unique pointer. Boost scoped pointer removed and went to STD unique pointer. Boost shared pointer went to STD shared pointer. And we implemented polyfills, STDX polyfills for Boost concurrency types. That's thread. There you go. Right. Thread, STDX thread, mutex, time mutex, recursion mutex. This is essentially, this is one of our developers, as he said, proposed plan of attack for how we actually get to the point where we're stable with both implementations behind a polyfill. Okay. Right, this is similarly for 14. The no except that we've been using until now, replace them in favor of true C+11 no except. Unified thread local storage, that's what I was discussing earlier on about the prerequisite for that, moving to Xcode 8. Stop linking Boost regex, stop linking Boost chrono, because we have SC implementations of them now, so we link them instead. And then this is an example, again, I really was overestimating how how high definition this was going to be. But that's an actual code sample from removing Boost thread. Right, finally, update the linting rules. So obviously, we lint our code and we can't actually commit anything until physically, because we have a bunch of GitHubs that prevent it. We can't actually commit anything until it lints. So in many cases, they'll update the linting rules to prevent us from referring to or from using older features that have been superseded. And after that, the platform team typically they communicate very well throughout the entire process of exactly what's going on. Obviously, they have to, but they'll basically communicate to their teams that we switched over, and they'll encourage other teams to start incrementally modernizing their areas of responsibility. Gently encouraging, typically. Sometimes they're more blunt, as in this case, where the query team received a ticket from one of our colleagues. Query DB exec code traffics in raw pointers. I like this. The reason I like this ticket is because you can almost hear the disdain dripping off this title. And also he's got code in DB exec, DB query makes very heavy use of exception unsafe new expressions and raw pointers. I have a patch. It's clearly irritated him so much that he just had to like dive in and fix it. We decided we'd do it ourselves incrementally, just to be on the safe side. Okay, so moving on. So how does this work practically? What impact does it have, and how does that map to the motivations that I outlined at the beginning? So I'm just going to go through a couple of very quick examples of cases where real cases, real problems, real issues, tickets that the query team had to deal with, where the availability of modern C++ was, at the very least, helpful and, really, in some cases, necessary, or very nearly necessary. So, oh yes, I forgot I had the slide. So this is basically what I just said. After platform's initial updates, modernization proceeds incrementally. Stable tenured code, we want to avoid upturning that all at once. Sometimes we do schedule and plan explicit modernization and tech debt work, but typically incremental changes towards the new standard are driven by a couple of factors, predominantly among them performance, correctness, opportunity if the opportunity arises, necessity, and convenience. So here's an example. We found that our blocking sort was less performant than we would like. Blocking sort is essentially, how many people here worked on databases specifically? Okay. Blocking sort is basically where the user is issued a query and requested the sort, and the sort cannot be serviced by the index that the query may be using. That means that we essentially, despite the fact that the query itself might be using the index and returning results quite quickly, filtering results quite quickly, we have to essentially sort the entire result set manually rather than just getting them back in order. And this is what we found was slow, slower than we wanted it to be. So we did what anyone would. Sorry.
So what sort of algorithm are you using? What was the sort of sorting algorithm that was so slow?
Oh, I think actually for this we just.
To sort.
No, it wasn't a problem with the algorithm. It was, but we actually profiled this. Well, I mean, not me personally, but we profiled this code, and we found that the real bottleneck was in actually every document you get back, you have to actually go into the document and extract the keys to be sorted. So basically, whatever they specified for the sort, and we found that was where the bulk of the problems were. So. Having pinpointed, this is where it was going. This is where the problem was, the bottleneck was. We were kind of eager to find ways to improve it. So this is the code that this is the change that we eventually came up with. Nope, that's it. This is very anticlimactic.
No change at all?
There. Again, this is, you can't see it, but basically we discovered that there was one place in the code where we were passing a vector, two vectors, in to a function to extract the keys in a way that results in a copy. So we basically just changes to a move, because we're done with those vectors at that point anyway. And let's try this again. So this change saves 2 vector copies and calls to tcmalloc delete. So we found that for large-scale sorts, it improved performance by up to about 40%, just this change. 300 milliseconds versus 500 milliseconds. So it just is an object lesson in how easily performance savings can be achieved with the new features that are available. I'm going to give up on this. Oh yeah, okay. So as I said, opportunity is another reason why we engage in this modernization work. In another case, the query planning and execution engine is one of the kind of at the heart of MongoDB. It's very, very, it's really at the core of the system, obviously. It's relatively old, quite tenured code, it's quite stable, but as we saw earlier, it does traffic in raw pointers. And one of our build variants is our CI system runs an address sanitizer and a fuzzer. The fuzzer is basically, it takes our tests, which are written in, integration tests are written in JavaScript. They use the MongoDB shell to spin up clusters, to perform tests, to verify that everything's working as expected. What the fuzzer does is, it takes our tests and permutes them and basically throws nonsense at the server. The goal basically is to verify that the server correctly identifies it as nonsense and rejects it, rather than invarianting and aborting.
Flushing protocol or something. Flushes. It's like a flushing protocol or flushing whatever.
I'm not sure.
No, like you said, it kind of signals to you back if the jargon you sent in came back to you, so it means the flow is okay.
Well, for the most part, we'd expect that, like, if you give it nonsense, then you'll get back an exception saying this was nonsense. Yeah. Stop. What the criteria basically here is that it will either the operation will either succeed correctly and not result in any adverse output, adverse side effects, or it will fail, and it will fail cleanly, and you'll get back the operation will fail, but the server won't fail. Right? So you're throwing random nonsense at it, effectively random nonsense at it, and if you hit an invariant, it's very good at finding basically edge cases that otherwise, you really never think of. So in this particular case, what we found was, towards the start of the year, that the address sanitizer, when the fuzzer was running on it, would occasionally result in some minor memory leaks. So leak sanitizer directly to 40 bytes one object in the query planner, and this was happening very rarely, but it happened a couple of times. So we looked into it, or I should say that one of my colleagues on the query team looked into it, and having already been admonished, as you saw earlier, for our lackluster modernization of the query system, he decided that rather than just fixing this particular problem, he would instead rewrite the query system to use managed pointers throughout. So, I don't know if you can see here, but this relatively small problem resulted in a patch that was 216 files changed, 226 additions, and 700 and something deletions. So basically, this is something that we were going to have to do at some point. This presented a perfect opportunity to do it. So Dave Storch, who's one of the members of the query team in New York, bit the bullet and went through it all and modernized it. And we have not seen this since. Okay, another example. This is an example where the availability of modern constructs enabled us to easily solve a problem that might otherwise have been quite tricky. So the view catalog in MongoDB. Views in MongoDB, non-materialized views, are essentially a predefined aggregation over a particular collection that are presented to the user as a collection itself. So you can do queries on this view, you can do aggregations on this view, and what will happen under the hood is that the aggregation that's defined in the view will be applied, and then your query or aggregation will be applied to the results coming out of that pipeline. The view catalog holds the metadata for all the views in a particular database. The name of the view, which is the equivalent to a collection from the client's point of view. The pipeline, aggregation that defines the view, and the underlying collection that the aggregation will operate on when you invoke it. New views typically added in the same way that collections are via the create command. However, because the view catalog itself is actually stored as a collection called system.views, it's also possible to insert a view definition directly into this collection, and that's legal, and it will be accepted as a view, and the view will appear to clients from that point on. So this latter use case led us to a very unexpected synchronization problem. So say, for instance, thread A calls view catalog lookup that obtains a view definition, so that it now knows what collection it actually needs to run on and what pipeline it needs to run on that collection. It holds a mode IS lock while using this view definition pointer. Mode IS is an intent lock. So in MongoDB, we have a multi-level locking system where essentially each operation that comes in takes an intent lock at every level global database collection down to the point at which it's actually going to read or write something. So a mode IS lock is an intent lock. It means that basically the operation is going to read something at the level below this. This is because in WiredTiger, for instance, we have document level concurrency. So basically for reading, we only ever intent lock a collection. So basically operations can operate on different documents within the collection at the same time without tripping over each other. That seemed like a digression, but that's relevant later on. So at the same time, thread B inserts a valid view directly into system views, despite the fact that this has a read lock on it, and read intent lock. This is possible only because the insert acquires a mode IX lock rather than in the ordinary case where you use a create command would be a mode X lock, which is entirely exclusive. Nothing else can access the collection while it's doing it. A mode IX lock is again because in this document level concurrency, you can be reading from one document while you're writing to a different document, that's fine. But because of this, and because it's this special system of views collection, view catalog valid is marked as false, indicating that it needs to be refreshed. Then when the third thread comes in and calls any method of view catalog, the catalog implicitly gets reloaded. That clears the old map of view definitions and releases all the view definitions. It invalidates all the iterators on the view map and frees the view definition pointers. Unfortunately, thread A still has its view definition pointer, and if it uses it, we get undefined behavior. So, as I said, this was an unexpected synchronization problem because the person who found this issue was typically expecting that this more formal way of doing view creation would.
So when you go through the create command, what does it do differently that avoids this?
So the create command, because it's creating a collection, will actually take an entirely exclusive lock on the database. So rather than just saying, I'm not really locking this, I just want something below it, which is an intent lock, it says, no, I need exclusive access to this, and nothing else can get it.
So it locks until thread A is finished with its catalog?
Yes. Typically that would be quite a short time, because thread A just gets this, starts the operation, and releases it immediately, and then this can do whatever it needs to after that. But basically, we don't want this to we want this to be an intent lock. This is an unaccounted for case, or was originally, because the view catalog is being accessed by a lot of queries at the same time in order to actually find out what the view is. Oh yes. So the problem here is that this could have been quite tricky to solve, because we don't obviously want to change the entire locking mechanism of MongoDB just to account for this case. So we can't change the IS and IX thing. We could ban people from inserting directly into system of views, but that would be a breaking change, and people, customers are already doing it. So it's not something we want to mess with. We could add additional, we could hold a mutex internally in the view catalog or something similar, but again, that's introducing additional locking, which we don't want because the view catalog is going to be very busy. So again, having looked at this problem, the engineer who figured out that this was an issue decided to go ahead and just refactor the entire view catalog to use shared pointers instead of the raw pointers that they previously were using. So a checked out view definition, thread A in this case, now gets a shared pointer to pointing at the view definition, while the view catalog retains its own one. If this happens again, so checked out view definitions will persist through a reload because the shared pointer will now have a ref count of 2. When the catalog gets refreshed, it will release its hold on the shared pointer, but thread A will retain that shared pointer until it's finished with it, at which point the ref count will decrement to 0, and it will do so at that point. This is safe to do because this is correct even if the view is removed, because basically once A has the view pointer and it has a copy of it, sorry, a reference to, I suppose, it then knows everything it needs to. It doesn't need to have any further interaction with the view catalog. So if it's refreshed, deleted, anything, the view definition is still valid at the point where A retrieved it. Now, if the other collection, the underlying collection has been deleted in the meantime or something, obviously that's, it's going to not return any results, but that's fine. That's correct behavior again. So this is just a case where a relatively tricky problem had a fairly simple solution. All it took was just basically refactoring the entire catalog to use modern concepts. All right, one more example. Match expression optimize. Match expression is an abstract syntax tree, which is produced by the query planner by parsing the client's query. So it comes in, we parse the Mongo query language that's defined in the query, and we get back an abstract syntax tree like this. I don't know if you can see this. Basically, it's and match expression, equality match expression, and match expression, greater than match expression, less than match expression. So there's a bunch of different types of nodes in this tree, each of which has its own operation that will return a match or not. Each of them has an optimization that, depending on its position in the tree, can be applied in order to simplify it. So to give an example here, so things like absorbing grandchildren, pruning redundant branches, and so on. So in this example here, for instance, we have an AND match expression, which one of whose children is itself an AND match expression that has 2 children here. So this one here is redundant, and when we optimize this, these two will basically pulled up here to the same level as the equality match expression. The query is still identical, it's just simpler and faster to run. So previously, all the optimization logic was in this canonical query class, which owns the match expression tree. So, and basically it was, I don't know if I can actually, it was, there you go. I don't know if you can see this, but it's essentially a very large if-else. So basically, it goes through each of the nodes in the tree, and it applies the optimizations appropriate to its position in the tree. But it means that essentially all of the logic for each of the node types is all centralized in this canonical query class that owns the match expression tree. So aside from being not an ideal design, that is, it came into contact with some of our goals for, I think I've messed this up now. That's right. Aside from being not very good design, it came into conflict with some of our goals for one of the projects we were doing in 3.6, expressive lookup, which is the ability to specify a MongoDB's equivalent of a join onto a foreign collection and perform any query or transformation on the documents from that collection and absorb them into your current aggregation. We also were introducing this $expr feature, which allows you to use aggregation expressions in the find query language. So basically all of this all meant that we had the need to call optimize on match expressions directly and have the optimization percolate down through the tree rather than have this big if-else statement that handled everything. And all optimization logic should be internal to each match expression. So each match expression knows how to optimize itself rather than relying on a separate class to implement that for them. So the problem that my colleague who ended up implementing this ran into was that the optimization could result in a node removing itself or being removed from the tree. So this meant that obviously, could get very complicated in a very complex tree. So we wanted to make sure that if that did happen, that we correctly cleaned up the nodes. So that implies that we wanted to use basically unique pointer semantics there. However, we also needed to have the optimize function basically refer to itself or take a pointer to itself. But basically you can't define a member function that accepts a unique pointer on the object itself, that you're, this object. So the problem was really that we had to come up with an alternative solution to implement this to meet all of the goals we had, the design parameters. So the solution that this guy came up with was quite nice. It involved a combination of a number of different modern language features: unique pointer, lambdas, and STD function. So all of the pointers, all the nodes in the tree, we did implement them so they're managed by unique pointer, so they auto-destruct if they're removed. We introduced a new pure virtual function into each match expression node called getOptimizer that returns an expression optimizer function that maps from a unique pointer match expression to a unique pointer match expression. And then this is an example of this, this expression, an optimizer function, is basically a lambda that takes the unique pointer and returns the same pointer itself. This is basically a no-op. This would be in a node that doesn't have any optimizations. But basically this function could return an unchanged pointer to the node itself, a mutated node, or a completely different node, in which case the previous node, now redundant, would be removed from the tree. So the way that this works now is that we obtain, from the root of the tree, we call getOptimizer to get the actual optimization function. Then we apply it to the node. It recurses down through the tree, optimizing each step as it goes. Each node may return the same expression, a mutated expression, or a different expression. Each match expression only knows its own optimizations. And so this approach, using these three constructs, achieves the desired goals of the project: virtual dispatch, all the logic internal to the nodes themselves, and managed pointers. And it allowed the match expression AST to be optimized in a similar manner to how we were already doing optimization in the aggregation framework, which itself was kind of a more modern approach. Okay, so where are we at the moment? This, you might remember the relatively small epics for C++ 11 and 14 that I showed you earlier. This is the epic. This isn't even the full epic. It's part of the epic for the move to C++ 17. Plans to move to C++ 17 are already in motion. Provisionally, we're targeting MongoDB release 4.2. As I mentioned earlier, we've already mocked up a couple of C++ 17 constructs that are in use in the code base at the moment to ease the smoother transition. Some of the language features that I'm particularly looking forward to: automatic template type deduction, which I think will be very nice. It'll save a lot of characters. Structured binding declarations, which will more or less make writing C++ look a lot like JavaScript. If and switch initialization. This doesn't seem like a big one, but I think it's there's so many times that I've been writing some code and I'm like, why do I need this extra line? Now I don't have to. And of course, SE optional, which will not be a massive change in terms of the code, but it'll be nice to actually have an official standard.
Now, what effect will this have on your minimum compiler support? So your MSVC minimum version that you require?
I'm not actually sure what version, the minimum version that it would need to support. It's probably actually in one of these tickets, but I'm not sure exactly which one.
So your GCC, so this,
yeah.
Will this still compile on Red Hat, for example?
Well, yeah, we won't proceed with it until we have a toolchain in place that will build everywhere that we currently build, which includes Red Hat. The problem is that, like, basically, toolchain changes and updates motivated by moving to the next standard are part of this whole process. They're typically done as close as is possible to the start of the development cycle, unless further problems present themselves later on. But as I said, like at the start, for instance, when we were thinking of moving to C++ 11 initially, we held off on it specifically because we weren't confident of that all of our compilers that we needed to work fully incrementally spec. So in terms of when this can happen, when this will happen, it's targeted for 4.2. It'll probably come in at some point during, as I mentioned, during the 4.0 development cycle, or towards the end of the 4 development cycle. Platform team. I asked them about this, and they said very soon, TM. So that could be really anytime. Okay, right. This is a slide that I didn't put on the content page, so I thought I'd just spring it on you. We're hiring. There's a position open for a database server engineer on the query team here in Dublin. Careers Department Engineering on MongoDB.com. In addition to this, there's actually, we also have an Ops Manager development team here as well. Ops Manager is our monitoring and management offering for MongoDB, so it automates deployment and managing and monitoring collection of metrics for other clusters. They're based here. They've already got a team of, I think, 6 people, and they're always on the lookout as well. So if you're interested, please stop by and have a look. And that's it.
Could you automate or consider automating any of this supporting with plan and tidy, for example?
Well, we use Clang format basically to.
I know Clang format is not the same as.
You're talking about Clang tidy in order to.
Clang modernize.
Yeah. Yeah. Not that I'm aware of. As I said, the approach that we've typically gone for so far is to introduce polyfills or kind of mock implementations as far as possible, so that we can actually have them in the code base and people start using them, and then when we change over to use the new features, then they're already there. I don't know whether or not the platform team has any plans to use Clang tidy or anything.
Are you aware that Clang tidy can be told to convert old code into your polyfill for you?
Yeah, I mean,
Okay.
but like, yes, but as far as I'm aware, we don't use it. I couldn't swear to it. Like, you know, I'll have to check with the platforms team. But I don't think we automate that.
Yeah, mine.
Yeah.
Do you find any semantic problems when you were doing this dual mapping between Boost and standard library in terms of, for example, you mentioned regex. So I mean, the Boost regex implementation is really high quality relative to some of the standard library implementations of regex. I was wondering, did you run into any troubles? Even in shared pointer, the Boost shared pointer is quite different from most of the standard library implementations of shared pointer. I was wondering, did you see any surprises, corner cases, weird quirks?
Well, actually, when I don't know if I can find the actual ticket here, but when the platform team was migrating to SC regex, for instance, there were a number of commits that specifically mentioned SC regex doesn't support this particular function, doesn't support this particular edge case or whatever, and basically in those cases, it was found that the use of Boost in that way in the code base was minimal, like maybe 1 or 2 tests. So they simply reworked those tests and proceeded to standardize on the SCD implementation.
Okay, interesting.
But generally it's quite smooth sailing, or it has been in the past. We'll see.
I'm just surprised. I mean, we argued about this one for some number of months / years, and we eventually decided to not do what you did, even though, I mean, Edward Diener and myself put that 2 alternative proposals on how to do that, but neither gained community traction. So it's interesting as a data point that that's great. Thanks.
Maybe one more question just before I have a quick break.
Hey.
So you build your code in the current version and the next version that you hope to.
Yeah, well, we build it for compliance with the current standard, but we make sure as well that we don't do anything that's going to actively break compliance with the next standard.
Measure performance, do you see a performance difference, or?
I don't have any. Well, for instance, when you moved to 14, we expected and saw a small performance boost due to the improved return type optimization, or rather fallback to move. I don't have any good figures for when the move to C++ 16 happened. Because that was quite some time ago. But I'd imagine that was probably a more significant boost. At the moment, the change to C++ 11 was kind of like the new era, and then since then it's been basically kind of incremental quality of life improvements, or that's what we found anyway.
You also do the cross multiple license.
Yes.
Yeah. You basically kind of have this matrix of.
Oh yeah. Yeah.
You don't have any feeling for any performance gains of different C++ compilers and that across those OSs. Pretty measurable.
I couldn't swear to them at the moment. Like I'd have to go and actually dig up the numbers and see what they say.
Cool. Thanks very much. There's maybe a 5 or 10 minute break and we'll get on to the next talk. So go get some pizza.